Okay. Now, continuing on from, can you even see me? Continuing on from long division, we're going to look at the remainder theorem. So I guess you can think of the remainder as, yes, the value we're left with at the end of a division. And that's generally, going back to our thing here, so this is example 3. That's generally this term here, that's our remainder. And there's this theorem that states that if I have a random polynomial and I divide it by a linear expression, so that means like x minus something. So remember, polynomial, I divided it by x minus something. It says that if I were to input that something into my polynomial, that will tell me what the remainder is. That's a pretty bold statement. And the first thing you might think about when you look at that is like, yeah, no way, that's BS, as if it's that, as if that's a thing. But we can check. So I'm going to paste, please paste. I'm going to paste the working out. That was the third question we did in the heart of the video. And I looked at this and I was like, no way, there's no way it's that simple. So anyway, let's go. I'm going to add to the side here, P of x is my original polynomial, plus 4. Okay, now P of the thing that I'm dividing it by, which is 3, so P of 3, that should equal my remainder, apparently. So this should equal 28. So if I go, is it a minus? No, it's 3 cubed minus 3 plus 4. And so that's 27 minus 3 plus 4, which is 28. And it's like, how in the hell? How does that work? So all I have to do is get this number here. All I have to do is get this number here, put it in here, and that tells me what the remainder is. How does that work? Well, I think that's pretty cool. But actually, it's something you've already seen before. And it's a lot simpler than you might think. The reason we do this long division is so we can factorize it nicely. It's kind of like completing the square. Completing the square is a really weird thing, but at the end of the day, we end up with two things or one thing in a set of brackets, and then this loose remainder term. Now we're able to find this loose remainder term by just inputting P of A. So that's kind of cool. And it actually shouldn't be a surprise that this is a thing. So that shouldn't be a surprise. And I guess the more you think about it, the less of a surprise it is. So that's the only example I'm going to do, by the way. I'm not going to do anything else. I just want you to kind of think about what we've already done. So if you have the expression, let's write like this: P of x. I've got a polynomial. Let's call it x squared plus 5x plus 6. This is the most basic one. So if I were to try and graph this, the first thing I want to do is factorize it. So this thing factorizes nicely to x plus 2, x plus 3. So just quickly verify 2 plus 3 is 5, 2 times 3 is 6. So I can factorize that. Okay, that means if I were to draw it, so if I were to draw this thing, it cuts at 2 and 3. And I know that that's just a parabola, so it looks something like that. Okay, and because I was able to factorize it, that's nice. Now, I guess what you can tell from this is if I inputted x equals 2, no, x equals minus 2, if I inputted that into here, what would happen? Well, if I put a minus 2 into here, that would be 0, and so then this would equal 0, and that just tells me what my x-intercept is. So that should be no surprise. Now, if instead I had completed the square on this thing and I added 5, or I added 5, what happens then if I input a minus 2 into here? Well, my answer is just 5, and it ends up being the remainder. So this would be 0 times whatever that is. So my remainder would just equal 5. And it's actually the exact same thing as what's happening in this equation. So if I were to input a 3 here, then that's going to be 0. And so my answer is going to be this remainder, 28. And that's just how far up or down I've moved the graph. So it doesn't actually matter what's in my set of brackets. If I find like the opposite of one of these numbers, so in other words, if I put a minus 3 into there, or if I put a minus 2 into there, or if I put a 3 into there, just so that this thing equals 0, then what I'm going to end up with is my remainder. So I'm going to end up with this plus 5, or I'm going to end up with this plus 28. So that's actually where this kind of comes in. So That's called the remainder theorem. All it means is if you're asked to do a polynomial and divide it by x minus something, that something there is going to be, when you input it into the polynomial, it's going to be the remainder. That's all I really want you to get out of this video. So I'm not going to go any further. We can verify it for another question. So I could go this one. I could do it for this one. And it's a little bit different because I've got a plus here. So if I was going, so p, let's call p of x equals x cubed plus 5. And you can see that I already have my remainder as 32, so I should know what the answer is, minus 4. And I'm dividing it by, and let's just get it in that right form. So let's just have it so it says x minus something. So divided by x minus something, minus 3. So see how I've got x plus 3 and I've written it as x minus 3. Okay, so then if I were to go p of that thing that I'm minusing, so the minus 3, that should equal this 32. And I did this before on my calculator and I actually did get 32. So I think that's a pretty cool theorem. But that's it. You're just going to be asked a couple of questions. There's actually a proof in the textbook, but I didn't think it was that necessary to go over. I think it makes a little bit more sense to talk about it in terms of its graph, maybe. I don't know if that's more confusing or not, but yeah, that's it.